today we talk about knapsack problem. Knapsack problem is one of the important problem in algorithms theory because it's quite simple and it may occur in some various situations. So it looks so simple, so you can face it in various real programs. Like you have a real project, you need to optimize something, and the way you need to optimize this, it look exactly like a knapsack problem. So it's a good thing that you can recognize the knapsack problem and you know what you can do to solve the knapsack problem, and that what's maybe even more important, what you can do to solve the knapsack problem. So what is a classical knapsack problem? Every time. Classical knapsack problem looks like this. You have n items. Each item has some weight and some cost. So we have different weights and different costs. And we have a knapsack, and the size of this knapsack is some constant s. What we want to do is we want to put some of the items in this knapsack so that the total cost is maximized. So what it will be, let's say we take some items such that the total weight of these items is no more than s and the total cost is maximized. Pseudocodes on the home tasks. I read this comment, but I'm not sure what pseudocode you're talking about. Can you write me what exactly pseudocode do you need? I'll send it to you in direct message. What? So this is the classical knapsack problem. You have some items, you want to take some subset of these items such that the total weight is no more than s and total cost is maximized. Something like that. And the most important thing you need to know about knapsack problem, that it is an NP complete. What does it mean? We will discuss in the future lectures what does it mean exactly. For today's lecture is not that important. The important thing that NP complete is something that we don't know how to solve. And we actually don't know if it is possible to solve it. So there is no proof that it's impossible to solve, and there is no proof that it's possible to solve. So it's kind of strange class of problems, but for today's lecture, we will not talk about this. We'll just say that it's some class of problem which we don't know how to solve yet, and I think it's most possible that we will not learn how to solve them, because it will be some kind of disaster. So if you have some problem like that, and there is no additional constraints on anything, that most possibly that your problem is not solvable. But that's a bad thing. The good thing that in some situations it may actually be solvable. And one of the important situations when this problem is solvable is when everything is integer and small. So if all these numbers are small integer numbers, let's say if all, for example, if all weights are integer, and let's say s is small, by small I mean that you can have an array of size s, something like that. So s around 1 million is usually fine. Let's see. Just for reference, is about, like, let's say about 6. That's usually good enough. We'll talk about home task discussion tomorrow. Let's talk about lectures today. Okay. Now, if it is true, so if all weights are integer and the total size of the knapsack is pretty small, then what you can actually do, you can put the total weight of your elements as a parameter of your dynamic programming. What we will do, we will use the following dynamic programming. We will use the following dynamic programming. Maybe solve some more simple task. Let's go back. Let's solve some more simple task before we start this problem. Let's solve some simple task. So let's solve some more easy task. Let's say that there's no costs. We just want to maximize total weight. So for example, if costs are just equal to weights, then we want just to have the total weights no more than S and total weights is maximized. So let's solve this problem first. This problem is also NP complete, just for you to know. So if you have a problem like this without costs, but you just have the weights and you want to maximize total weights, but this shouldn't exceed the size of your knapsack, then even in this case the problem is NP complete. So let's solve this problem first. What you can do, you can do the following. Let's say that d of, for example, I and j will be the Boolean value which says if it is possible, to have subset of items from 0 to I minus 1 with total weight equal to j. So we have all these items. We take only first I items from this list and try to make a subset with sum equal to j. Let's draw this. So we have these some items. So these are items. We take, let's say, first I of them from 0 to I minus 1. And from these elements, we take some subset. Let's take, for example, like these elements. And the sum of weights of this element should be equal to j. So in this array, we'll have some Boolean value which answers the question, is it possible to take some subset with this, exactly this sum? Go. I'll finish this and then I'll draw a cat, okay? So how to calculate these values? Let's see, how you do it in dynamic programming. You kind of try to reduce your problem to the same problem of the smaller size. So what you can do, so if you want to have the sum equal to j from the first I elements, let's look on the last element, on this element, I minus 1. There are two possible cases. First possible case is if this set we're looking for contains element I minus 1. If our set contains this element I minus 1, then what we need to do, so we take this element in our set, and the total sum of all these elements equal to j. Then let's remove this element from the set. So we end up with some set of first I minus 1 elements, and the total weight of all these elements should be equal to j minus weight of this element. So if total weight of this element is j, then total weight of all these elements will be j minus weight of I minus 1. Let's say this. So if set contains this element, then we need to take from the first I minus 1 elements some subset with sum equal to j minus weight of I minus 1. That's all. And what if set doesn't contain this element? Contain -1. Then, if this element is not in the set, then we need to have some subset of first I-1 elements with sum equal to j. So this sum just equal to j, right? So the answer will be in D I-1 j. That's all. Now each time we there are all possible cases. Yeah, so we just cover all possible cases for the solution of the problem. Well, because the last element is either in the set or not in the set. So in both these cases, we have the same problem of smaller size. We already solved it in the previous iterations of dynamic programming. So we have solution of the first problem here, solution of the second problem here. Now we just combine these two solutions and get the solution of our problem. So the solution of our problem, the ij, will be equal to this solution or this solution. Or that's all. Should we write the code? That's actually mostly all the code. So just need to have two more loops here for I, for j, and so on. It's basically the whole code you need. Now let's have some example. For example, we have some items. Let's say so. The weights of the items will be. It's always hard to have a good example for the Knapsack problem. Let's say we have 5, 3, 2, and 6, and the size of Knapsack is there are all possible cases, right? We have 2, 3, 4, 5. Create this. Have another 3 here. Let's say size is 9. Yeah, good enough. So now, what we're doing here, we just have this two-dimensional array. So this table D. So the first index is the number of elements. It's from 0 to 4. And the second index is the weight of the elements. So the weight is from 0 to s. We don't need any weight to be more than s. So the second dimension of this array shouldn't be more than s. 5, 6, 7, 8, 9. Okay. Now, we start from the first row of this table. Now, the first row is simply the problem when you have no elements. So in the first row here, I equal to 0, so you have no elements. So the only subset of empty set is empty set. So in empty set, the total weight is 0. So for the problem with I equal to 0, we have solution when j equal to 0, and we have no solution if j is more than 0. Now, so we'll have, I have plus and minus. So plus is true, minus is false, and false here. Now, for I equal to 1, so what we're doing, we iterate for all values of j, and for each j, we use this formula to calculate the answer. For example, here, if the j equal to 0, so we want to have the subset of weight equal to 0 from first one element. We can do it, we just don't take this element. If we don't take the first element, we'll have the same problem as before. So here we have true because we have true here. So we have plus here. And here what we have this element of weight 5. So we can't take this element because we need the total weight to be equal to 1. So 1 is less than 5, so we can take this element. So we have no this part of the equation. And for this part, we'll have this cell. So we want to take 0 elements and have weight equal to 1. And it is not possible, so here will be minus. And also here will minus, here. Here will be the first plus, because here what we're doing, we want to have the total weight equal to 5 from the first one element. We can take this element, so we'll have this part. And we need to take some subset of first 0 elements, of total weight equal to 0. It is possible because here it is. So here we have plus. And here we have minus. Oh, plus is true, minus is false. I think it's kind of more good looking than the zeros and ones, no? Okay. Now for the second element, we do the same. We just go from left to right. So each time we're looking on two cells. So when we look on this cell, we try to look on two cells in the previous row. So here, if we don't take this element, we have this element. And we take the element, we have the position I minus 1 and j minus, so we have this, this. So this is j minus n. So when we construct the second row, the weight of element is free. So we look on two elements, the elements just above and element free position to the left. So here will be plus, minus, minus. Here will be plus because here is plus. Minus, plus, minus, minus, plus, minus. Yeah. And so on. We continue the same process. We take the element of weight equal 2. Do the same here. We can minus, plus, plus. Minus, plus, minus, plus, plus, minus. And the last one here is free, so we have plus, minus, plus. Here we have plus, right? Looks fine now. The only new weight is 6, right? We don't have 4, we don't have 1, and we don't have 9. Looks fine. Now, how to solve the initial problem? So if we want to find the maximal total weight, which is no more than s, we just find the rightmost true in the last row of this table. So this will be the maximal total weight which we can achieve. That's all. That's how you solve the Knapsack problem if the s is small. Now, what does it mean again? What does it mean? What does it mean this plus? This plus means that it is possible to have some subset of our elements with total sum equal to 8. It's the maximal weight less than s, less or equal. Cool. Now, if you want to actually construct a set, so if you just this plus just tells you that it is possible to have this subset. But what if you want to construct this set? You do it the same way as we did in the previous lectures. You just go from this last state of your dynamic programming and use the backwards links. Let's just to get the previous state in the dynamic programming. So how did this plus get here? It may get, so it's free. It may get from here or from here. Two possible cases, here and here. for example, let's say it's come from here just for some to make it more interesting. And this plus goes from here or here. Too many possibilities. And this plus goes from here. This plus goes from here. So what does it mean? It means that you, to get this sum, you need to take these three elements. So you need to get this element 3, this element 2, and this element 3. So total sum will be equal to 8. There are other possible ways. Yes, you can go, for example, from here, and here you go from here, and from here, and from here. There's other possible way. So you can take this element 5 and element 3. That's also a valid answer. You can calculate the number of possible answers like we did before. You just in each position you calculate not the Boolean value but the integer, which is the number of ways to get into this state. So it will, in the end, you will have the number of possible subsets with this sum, and so on. So you can apply all the techniques we used before just to this problem. So good. Now let's move to the initial problem. Let's move to this problem. So what if we have costs? We just do the same, but we just add the costs to the state of our dynamic programming. So instead of having the Boolean value, which says is it possible or not, we will use the number which is the maximal possible total cost of the subset with this sum. Let's change this. Let's say this is the maximal total cost for subset of elements from 0 to I minus 1 with total weight and with total weight equal to j. And now you use the same approach. We just have these two cases. For this new element, it's either in the set or not in the set. If it's not in the set, here, if it's not in the set, then we just have subset of I minus 1 element with sum equal to j. And if the last element is in subset, then we have this maximal sum for all elements here and plus the last element. Like this. So in the end, we'll end something. So now we just take maximum of these two values. Let's write this. Maximum of the I minus 1 j plus weight I minus 1 plus c I minus 1 and d I minus 1 j. Something like that. Cool. And let's have another example. Let's have, for example, let's have some costs. Well, let's have some special cost. We have this cost 3, let's cost 1. It's free stood. What I want to do, I want this cost to be here. I want this cost to be more than this cost, right? I will have some small numbers here, like 5, and this will be. Good enough. Yeah, good enough. Now, For some state, it is impossible to reach this state. So for some state, it's just impossible to get any subset with this sum. For these subsets, you can do it in different ways. You can make some special mark that it is impossible to reach the state, or you can put some special value, just like minus infinity, to the positions which are not achievable from the starting position. So if this set is empty, so if there is no subset with sum equal to j, you just put minus infinity, because minus infinity is neutral element for the maximum operation. Small tricks. So you just go from right again. You go from top to bottom, from left to right, and just fill this table with these values. Again, first row is just the empty set of elements, so you can get sum equal to 0, the total cost equal to 0, and all other states are impossible. So you just push minus infinity in all these positions. Can I just put minus here also? Minus infinity is too complicated to draw. That's all. Now, here you just use this formula to calculate the solution of your problem. Just go from left to right again. Calculate each time you take the cell just above and the cell positions here. And don't forget to add this value when you go from this position, because here you add one or more items, so you need to add the cost of this item to your total cost. Let's go so from here. 3, so 2, 3. Now we have item with weight equal to 3 and cost equal to 2, so 0, 2, 2, 2, 2, 3, 2, 2, 5, right? 5. I'm very bad in arithmetic actually. Now we have item cost with weight equal to 2 and cost 5. So we start from the right from here, say 0. That was complicated. Here we have 5. Here we have 2. Here we'll have the minimum of 2 values. We can either get this value, so get this value 3, or we can get this value plus weight 2. So what will the maximum will be from here? So here we have cost 2 plus this element will be cost equal to 7, right? So here the maximum of 3 and 7, it will be 7. And so I go from the back here, and here's 8, 5, like this. And the final, let's finish this. So it's 3 and 3, so it's 0 minus 5 here. Maximum is 3. Right? We have 2 here and 3 here. None here. Here we can go from here. It will be 5 plus 3 is 8. It's more than 7. Here we have 2 plus 3 is 5. Here we have 8, right? Here we have 5 or 7 plus 3. It's 10. Looks fine. So the answer is 10. Again, how to find the answer for this problem is slightly different. Here we need to find the maximal possible sum of total cost. So to find this total cost, you just need to iterate on all values of the total weight and find the maximal value in this. So we just take the maximal value in the last row and j, or all j from 0 to s. And again, how to find the subset? You do it in the same way. You go from the last state of your dynamic programming and iterate to the first state of your dynamic programming. And when you go back, you find the items you need to take to get into this state. So to get into this state, we go from this state. To get into this state, we go from this state. To get here, we go from here. To get here, we go from here. So to get this sum equal to 10, we need to take this item, and this item. So it will be these three items. And total cost is actually 10. Yeah, that's correct. No, that was pretty fast. Cool. So that's the first of the problem. This is the first situation when you can solve the problem when you face the problem of Knapsack problem. If all weights are integer and the total weight is small, then you can just, again, what is the trick? The trick is very simple. We know that this total weight is small. So here, total weight is small because the total weight shouldn't exceed s, and we know it's integer. So not so many cases. So for this total sum, there are not so many different cases. So we can just have array of the size equal to s and find the answer for all possible total weights from 0 to s. And if s is small integer, it will be good enough. Let's calculate time complexity. Yeah, the time complexity will be something like. So we just all this on an array and calculate in constant time, right? So it will be n multiplied by s. That's all. Cool. Why did I say first that it is incomplete? So it is kind of impossible to solve it fast, because you can easily make a big number. So if number s is big, then you cannot do it, because you cannot make array of size s, you cannot spend s time to calculate the program, and it's quite easy to make a big number. You can just say that s equal to 0 and many zeros. It's quite easy to write a big number. You just write many zeros and number is very big. In the problems we discussed in previous lectures, we have opposite situation. The complexity of the program depends only on the size of the input. So if you have like in which problem? What we're talking about? We talk about text justification and Levenstein distance, right? For example, in Levenstein distance, when you need to calculate Levenstein distance, you need to time complexity depends on the size of these two strings. You have two strings, and time complexity is just multiplication of the sizes of these two strings. You can't make string of this size. Yeah. So in the previous problem, if you have one of the parameter big, it means that you actually pass the big array to your program. So you can't pass too big array to your program because you don't have enough space to write program. But you can easily get one big number. It's easy to pass you a big number, but it's hard to pass you a big array. That's basically the difference between why this program is called slow and this program is called fast. Yeah. Again, we'll discuss some topics about time complexity and complexity classes in one of the future lectures. Not sure in this semester or in next, but at some point we'll discuss what is it and why one problem is considered to be good and another problem is considered to be bad. Not today. Any more questions by now? Let's draw some cat. I promised you to draw a cat. Let's hold cat. Good enough. Okay, are you still here? It's too quiet in the chat. Good. Now, do we have enough time? Do we have enough time? I'm not sure if we have enough time. We'll talk about it in the home task here. And another important case is, for example, if you have the weights, if weights are big or weights are not integer, but these costs are small. So if this total costs, I just mentioned it, and we'll discuss it in the home tasks, I think. So, for example, if this total cost is pretty small, so if this total cost is small integer and costs are integer, then it's also possible to solve the Knapsack problem efficiently. Let's leave it to the home task because it's kind of it's not that important, but it's kind of interesting to discuss it for you in the practice. Basically, you need to do the same thing, but instead of having the total weight as a state of your dynamic program, you have this total cost as a state of your dynamic program, and then you solve the problem in the same way. So I will leave it you for as an exercise, and I will just move to the next topic. Now, what is the next important topic I want to discuss is what to do if you have problem with all costs, like all weights are not integer, if weights are too big to have this array of this size. What you can do? Several different things. First, what I want to talk about today is what you can do if the number of items is very small. So if n is very small, again, you're too quiet. Can you write something in the chat just in 30 seconds? Just keep sure that every 30 seconds something is going on in the chat. Because last time when chat was frozen, it was because I lost the internet connection. So I need to have some indicator that everything is working. Okay, now let's go back. So what happens if n is very small? What I mean by very small, for example, if 2 in power of n is somewhat small, small enough, let's say. Yeah, now, so what you can do? Well, let's say, for example, if n is about, I don't know, 25, then 2 in power of n will be about 32 millions. It's small enough. It depends on what do you mean by small. So if you have a nice computer and you have few days to solve your problem, then you may say that n is about, I don't know, about 40. I think for n about 40 you can spend few hours, I think, on a regular computer or few minutes on the good computer. So it depends on what computer do you use, but about this. So what you can do to solve the problem? Well, it's quite easy. You can just iterate over all possible subsets of your items. So iterate over all possible subsets. There are 2 in power of n possible subsets. You iterate over all of them and take the optimal one. That's what you can do. Now, how to iterate over all possible subsets? There are various different ways to just iterate over all possible subsets of the given set. One of the way is to make a recursive procedure. Will we talk about this later? It's quite common way to generate something. You make a like backtrack. So you guys like take two possibilities. You take the element or you don't take the element, and then you recursively call the same procedure for the rest of the elements. I will not talk about this much more. But what I want to discuss today is the easiest way to iterate all subsets is just enumerate all the subsets, because it's very easy to enumerate all the subsets. How to enumerate all the subsets? Let's make a bijection between the subsets of elements from 0 to n minus 1 and integers from 0 to power n minus 1. The subsets are very easy to enumerate. How to enumerate a subset? Let's take a number like this. It has some bits, so you have n bits in your number. So here we have subset. Let's have a subset x equal to, I don't know, elements 1, 2, and 4. How we'll get the integer which corresponds to this subset? Very easy. We will build a bit number which have 3 bits equal to 1 in these positions. If you look on bit number, we have x. Let's have it has some n bits. We'll say that all bits are 0 except these 3. So we have this bit in position 4, this bit in position 2, this bit in position 1, like this. The positions of bits are usually counted from right to left because that's how numbers are right. Yeah, right. So this is the least significant bit. This is the most significant bit. Like it's usually done. So numbers for bits are usually from right to left. So this is bit 0, 1, 2, and so on. This is bit n minus 1. Yeah. So this subset corresponds to this integer number. So this integer number, let's say it is 2 plus 4 plus 16, 22, right? Base 2. Good. Now, again, you stop posting anything in the chat. You forgot how to do it. Let's exercise. Now, write something in the chat. Good. Keep doing it like every 30 seconds. Cool. Now, let's try to make all common subset operations using these bit numbers. What you can do when you want to operate some sets, you basically have some basic operations. Let's say how to create a subset of one element. So if you want to create set of element I, how you do it using this bitwise representation? It's quite simple. You need to make an integer with 1 bit equal to 1 in position I. In most languages it's done like this. You just have 1 shifted left to I positions. What else? For example, if you want to make a union of two sets, x unite with y. How you do it in this bitwise representation? Quite simple. You need to make the bit number which have bits in the positions when at least one of these numbers have 1. So you have the bit should be equal to 1 if at least one bits in x or y equal to 1. That's just the bitwise OR operation. So wait, x or y, like this. It's slightly different in different programming languages, but usually it's like this. In C++ it's like this. The same for intersection. If you need to intersect x and y, then simply it's x and y. The difference is slightly different. So if you want to have x minus y, so you take all elements of x except all elements which are in y. You can do it. The easiest way I know how to do it is like this. Into x and not y. Like this. But in some simple cases, for example, if y is subset of x, so if y is subset of x, then you can do it in a more easy way. You can do it like this. You can say x like minus y like this. Because you have ones only in positions when you have x, ones in x. So if you just subtract one number from another, you will have the correct difference of the. Or you can say x XOR y. That also works. It's about the same time, so it's not a big difference. Just what do you prefer? I usually prefer to have minus, just because it's like more natural to have. I need to have the difference of two arrays of two subsets. So it's like x minus y is the difference of these two arrays. What else do we need? Also, we need to check that element is in the subset. So how to check if element I belongs to subset X? Well, easiest way to check this, like two schools of this. I usually do it like this. I just check that I have X and I intersect X with I1. So what I want to do, I want to intersect the set X with the element of one, with this one element. So I intersect X with the set containing only element I. So if this intersection is not empty, then element I belongs to set X. Another way of doing this is like this. You can omit this greater than if you're writing in C++, something like this, so you can just say X and 1, something like that. Another way of thinking about this is like this. You can take now this bitwise X, then shift it right I positions, and then end with 1. So, like this. That's your like personal preferences. Like, decide which one do you like most with and use it. That time is about the same for both these operations. So it's only your personal taste. Good. I think it's good now. Now, how to solve the problem? Again, we just simply iterate over all possible subsets of n elements, and for each subset, we calculate the total weight, total cost, and get the maximum. I'm drinking tea. No. Vodka's not today. It's too early for drinking vodka. So we iterate over all subsets. It's just easy to iterate over all possible sets. You just iterate over all numbers from 0 to 2 minus 1. So for x from 0 to 2 in power n minus 1. We take this set and then we calculate the total sum of total weight and total cost. So calculate these two values. Let's say like this. So equal to 0 as is equal to 0, then iterate over all elements, check if I belongs to X, then like this. Here I'll write something like that. So I just, for simplicity, so this represents. So here I use this thing just to make shorter program for the whiteboard. So here we just need to check that element belongs. You just use one of these formulas to check that element belongs to this subset. And that's all. Now you calculated the total weight and total cost. You check if total weight is no more than S, no more. And then you update your answer with some result. Like this. Yeah. Yeah. I think it's pretty nice program. Now, what is time complexity? Time complexity is quite simple. Here we have a loop of 2 power of n iteration. Here we have loop of n iterations. So no any breaks here. So the time is always the same. The time complexity of this program is 2 power of n multiplied by n. Nice. So in time complexities like this, usually what you want to optimize this left part, because if you have non-polynomial time complexity like exponential, usually you care only about this exponential part, because the polynomial part is usually small. Not always, but usually. So usually you don't care about this n, because n is small, so like 25 at most. But this left part is what you usually want to optimize. If you have another solution with better asymptotics here, it will be just better than any solution with any polynomial here. So let's write a bad solution. So what can we do in this program to have a bad solution? One of the approaches you can make is to do the following. This method called meet in the middle. What are you doing? You have these n items. What you want to do is to split these n items into 2 groups. Let's have this left group. Well, how many? About here, I think. And over 2 numbers here, and over 2 numbers here. Now you split each subset into 2 parts, left part and right part. So imagine you want to have the subset of some elements here and some elements here. I need another color, for example this, and some subset here. So I just split the array into 2 halves, and for each half I have these elements. So these marked elements are the elements I want to be in my subset. This is the optimal answer. Let's split them in the left elements and right elements. Let's say elements in the left part are x, and this subset is y. Now, what I want to do, I want to iterate separately. I want to iterate all possible x's, iterate all possible y's, and do it in 2 separate loops. Now, what I need to do? I want to have these 2 subsets, and I can rewrite these constraints in the following way. I need sum of all elements belonging to x Let's call it SX. It's too complicated. Let's say WX. It will be the sum of all weights of elements in the subset X, yeah? Plus sum of all elements in subset Y should be no more than S. And cost in X plus cost in Y should be maximized. That's, I don't like this. Let's call it S1 and this S2. So I iterate for all possible subsets X and put this total weight in some array. So let's say V1 of X plus W2 of Y is no more than S, like this. So this is the total weight of elements in subset X. This is the total weight of elements in subset Y. The sum of this should be no more than S, right? You forgot to post in the chat. Shame. Now, and the total cost should be maximized. C1 of X plus C2 of Y should be maximized. That's what we want to do. And so we want to find a pair X and Y such that this sum is no more than S and this sum is maximal possible. How can we do it without iterating all possible ways? If we iterate over all possible pairs, we'll have 2 in power of n over 2 here and 2 in power of n over here. 2, the product of these two will be 2 in power of n, so it will be the same time complexity. But I want to optimize this in a way. I want to not to iterate all possible pairs, but somehow to find for each x the optimal y. So, may I just skip the part when I can calculate this number? So you calculate these numbers using the same technique. But what should you do next? What should you do next? I want to do the following. I want to iterate for all possible x's. So I iterate for x for 0 to 2 in power of n over 2 minus 1. And for each x, I want to find the optimal y. How to find the optimal y? No, let's look. If we fix the value of x, what constraints do we have on y? Let's see. No, from the first equation we have something like, so I fix the value of x, so I need to have w2 of y be no more than s minus w1 of x. And from the second constraint, I just need to maximize the value of C2. Yeah, this is called meet in the middle, yes. Now let's think, can we solve this problem faster than just iterate for all possible y's? Is there a way to solve this problem fast for each x? It actually is way. There are two possible ways actually. One of the ways is to sort both arrays and have 2 pointers method down like this. Or you can have a binary search. What you're doing? You find all the values of y. Then put these values in some array. So you put these pairs, total weight and total cost in some array. And sort this array by W2. So you sort y's by W2. Then in this sorted array, here you will need some prefix of this array. So here you have some elements with W2 no more than this x minus 1. So here you always the available set of y is always the prefix of this array. We need to go. And for this prefix, you can find this prefix using binary search. Yes, we discussed it in lecture about binary search. You can find this prefix using the standard binary search. And now you just need to find the maximal value on this prefix. You can do it. You can pre-calculate the maximal value for each prefix. So now you just use binary search to find this prefix and take the pre-calculated value of this prefix of maximum value on this prefix. That's all. So you do the binary search in logarithm time and then just take the maximal value. So what will be time complexity? Time complexity will be basically we need to have this array. We need to have this array of size 2 in power of n over 2. And then you need to sort this array. To sort the array, you need n log n time. But n is equal to 2 in power of n over 2. So logarithm of this is n. So time complexity of sorting will be something like this. And also this, you need another logarithm here to find this prefix using binary search. Binary search works in logarithm time. Logarithm is n. That's much better than the previous algorithm. Again, the difference is huge actually. So we get from this algorithm to this algorithm. So we decreased, we optimized the part of this time complexity which was not non-exponential, well, it was exponential. So it's usually a big difference. For example, in here, now we can solve the problem for much bigger n. For example, for n equal to 50 normal substance, or even up to 100. No, 100 is big enough. No, you don't have to build the array of size 2 in power 50. But 2 in power 30 is absolutely good enough. Well, how many data you can put in one array? Let's say you have terabyte hard drive. You can put about, if you have 4 bytes for integer, you have like 200 billions of elements, right? So we need logarithm of 200 billions. It's like about 37, 38. Yeah. Questions. W2 is the total weight of all these elements. So the total weight here is W2. So iterate over all elements in this right half of this array, all subsets here. And for each subset, calculate the total weight just by simple iteration and put this answer into this array. Yeah, you can rewatch a lecture about binary search. Binary search is one of the most important algorithms actually. So if you don't know how to use binary search, that's one of the first things you need to learn. Cool. Now, the final problem I want to talk about is a little bit different. Let's remove this, remove this, remove this, remove that. Yeah, you sort y's by these values. You have arrays of all possible y's. So y is, so you iterate through all possible y's. So y is here from 0 to 2 in power n over 2 minus 1. So you get all possible subsets of the right half of the array. For each subset, you calculate its total weight and its total cost. Put these pairs into big array and then sort this array. By the key for the sorting is this value of weight. because you want to have some prefixes here. So you need to array sorted by the total weight. Yeah, clear enough. Is it clear enough, right? Again, what you do here. First, you iterate all possible values of y. For each value of y, again, y is subset of the right half of the element. You iterate all possible subsets. For each subset, you calculate the sum of w and sum of c. It will be the total weight and total cost. You put these two sums in two separate arrays, in w2 and c2. Now you sort these arrays by the value of total weight. And now you iterate over all possible values of x. And for each x, you can find this prefix of the second array just by binary search. So you know, so here in this prefix, you have all valid subsets of the right half the array. Such subsets which you can add to your subset x, so that the total sum will be no more than x, or no more than s. First, again, we have 2 in the power of n over 2 elements here, and 2 in the power of n over 2 elements here. So first we iterate here. Again, number of iterations is the same. Then they sort this array. We have, again, this time complexity. And then we do it here. So we have two separate loops. First loop is to iterate all elements here. And after this, we iterate all subsets here. Right, like two different. First, do something like this. So first you iterate for all y's from 0 to 2 in power of n over 2 minus 1. Do something. Then you sort something, and then you make the second for like this. Sorry, not nested. So you have 2 in power of n over 2 here, and another 2 in power of n. So they are not multiplicated. You have one section and then another section. Cool. Now, the final problem I want to talk about is somehow, I think it's a kind of bridge to the next lecture. We will talk about the following problem. So again, you have n items. They have different weights. And you have you have infinite number of knapsacks. And each knapsack has size x. And you want to put all your items in minimal possible number of knapsacks. Writing is difficult. Again, you want, there is no cost, there is just items. So you want to minimize the number of knapsacks. So let's say we have weights equal to, let's say 2, 5, 3, 1, 4, 8, and the s equal to, let's say 9. Then you may, for example, put items, let's say 5 and 4 here, items 8 and 1 here, and items and 2 and 3 here. Why not? So in each knapsack, total sum is no more than s. That's the problem. So this is like multi-knapsack problems. You have multiple knapsacks and you want kind of fill all of them in optimal way. The interesting part about problems like this, it is usually not solvable at all. So it's not, I mean, not solvable in the first way, even if these weights are small. So even if weights are small integer numbers, it's kind of hard to solve it. Just because you can have this sum as your state, because you have several different knapsacks and you kind of want to remember the sum in all knapsacks, the current weight in all knapsacks, not in one. When you have one knapsack, you can put the total or the current weight as the state of your dynamic programming. But here you have multiple knapsacks, so you kind of want to remember the state of each knapsack. So the total number of states in your dynamic programming grows exponentially, even if these weights are small. So how can we solve it? Let's solve it for small n again. Again, if n is very small, what I want to do, I want to put this, I want to put this subset as a parameter of my dynamic programming. That's slightly different from what we did before. So I want to have this d of x be the minimal number of knapsacks. Good enough. To put elements which belong to set X. So X is some subset of elements. That's slightly different from what we did before. Now we use this bitwise representation of subset as an index in the array. That's kind of different. But the idea is the same. We use, because n is very small, we can iterate all possible subsets and use this subset as index in our array of dynamic programming. So we use this x as a parameter of our dynamic programming. Now, how do we solve the problem? It's quite easy. So how to solve the problem? You have this subset x. You want to put all elements in this set in some knapsacks. So let's iterate our elements which you put in the last knapsack. So let's say you have some elements. Let's remove it here. Yeah. Let's draw it like this. I think it's... So you have several knapsacks. Schematic. Here you put all elements of set X. Let's iterate our elements which you put in the last knapsack. So let's say that here you put all elements of set Y. Let's iterate all possible sets Y which you can put in this last knapsack. Then how many knapsacks do you need? Then you need one knapsack for this last Y. Let's just do it like this. E of x will be minimum for all subsets for all subsets of x, such that sum of all elements in subset Y is no more than s. So we just iterate all possible subsets of x which you can put in one single knapsack. Now you put these elements in one single knapsack, and now what you get, the rest of the elements you need to put in some other knapsacks. But it is the same problem of the smaller size. So the answer to this problem is 1 for this plus d of x minus y. Like this. So that's how we will solve this. Again, it's slightly different from before. We use this subset as a parameter of our dynamic programming. And here I use this D of some set. X is the set of elements. But we just enumerate all the sets with integer numbers. So we can use this set as an index in the array. And here we just recalculate this value using iterator all some subsets of X. Now, let's see. Let's write a simple program. Let's write a simple program. What we can do, iterator all X from. We need some base, yes, right? So let's say D of 0 equal to 0. Yeah, then it can be done. Yeah, it's quite important to see the difference between problems you can solve and problems you cannot solve. That's actually one of the most important things you need to learn from this course, is that some problems you can solve efficiently, some problems you cannot solve efficiently. Yeah, that's actually important knowledge. Now, let's iterate all x's, so we have 0 here. Let's start from 1 to n power n minus 1. Here I need to iterate all subsets. I'll do it in a simple way. I just iterate all y's from 1 to 2 n power n minus 1. Check if y is subset of x, and sum of all elements in y is no more than s. I'll just skip this part, right? You can pre-calculate all these sums before. So yeah, I'll just, for simplicity, I'll skip this. You can pre-calculate the sum of weights for all sets in another loop. And then you use this formula. You guys choose 1. Let's say d of x equal to mean x plus plus and d of x minus y plus 1. Okay. Good. That's all. That's a solution for the problem. Cool. So, what is the time complexity of this solution? It's quite simple. Again, we have two loops of size 2 in power of n. So we have 2 in power of n here, 2 in power of n. So total time complexity will be 4 in power of n. That's not very good. 4 in power of n is much worse than 2 in power of n. Yeah. So if for 2 in power of n we can have solution for n, let's say up to 30. Here we have solution for n up to 15. That's kind of sad, because the size of the problem you can solve is just decreased. But we can optimize this. Let's optimize this. The first thing we will optimize is the following. Here we'll optimize the second loop. In the second loop, we need to iterate all possible sets. We need to iterate only for the subsets of x. So here we need only the sets y, which are the subsets of x. So let's try to iterate not for all elements, not for all possible sets here, but only for subsets of x. Will it improve our time complexity or not? Let's check. So if we here iterate not for all subsets, but only iterate for all the subsets, let's change this like this. Subsets of x. I need to like that for y, such that y is the subset of x, like right like this. Okay, clear enough. So, and here I want to check that again, sum of y is no more than s. will it improve the time complexity if I change like this or not? It turns out it will. Why? Because let's check what is the total possible number of pairs xy. So here I iterate all possible pairs xy such that y is subset of x. So what is the total number of pairs like this? Well, let's check. So we need to have some set x and some set y, and y is a subset of x. Let's look on every element. So x have some bits here, and y have some other bits. Something like that. So this is the bit representation of x, this is the bit representation of y. For each bit, what we can have? We can have 2 zeros. We can have 2 ones. And we can have 1 and 0. That's all. There's 3 possible cases for each bit. Each bit is either not in. Sorry, what does it mean? It means that bit equal to 1 bit in element means that element is in the subset. So each element is either in none of the subsets or in both subsets, or it is in subset x but not in subset y. There are 3 possible cases for each element. Yeah. So if there is 3 possible cases for each element, then there are 3 in power of n possible variants to construct these 2 bit vectors, right? So the total number of vectors like this is 3 in power of n. So if we somehow manage to iterate not for all sets but only for subsets of x, we can improve this time complexity from 4 power of n to 3 in power of n. If it's subset, we can intersect them. Not sure what do you mean. No, I don't get it. I don't get what do you mean. How to iterate on all possible subsets of x? The easiest way I know is the following. So let's. I don't want to erase the cat, so I just erase this. Cat is more important than this. So we have this number x. Let's see. And you want to iterate on all possible subsets of x. It means you want to iterate on all possible bit numbers which have ones only in these 4 positions. Right? So let's try to iterate these numbers from largest to smallest. So I will iterate y. So the largest number is obviously x. Let's say x. And then I'll go from the largest number to smallest, so the smallest will be zeros. And I will try to move from here to here, each time decreasing the number. How can I do this? Quite easily. So here, what is the next maximal possible number which is the subset of x? Quite easily, you need to take, again, like you decreasing the bit number, you should find the rightmost one and decrease it by 1. So the next number will be 0. And now again, you need to move to the next subset in decreasing order, right? So you need to take the last one here, decrease it by 1, 0. And then from this position to the right, you add all ones in positions when there are ones in x. And so on. Now you get rid of this one. and put these ones back, and so on. So again, how do you get from one number to the next number? You do the following. Where is this? Don't need this anymore. So you have this x, and you have the current y. You want to move to the next value of y. What we need to do is to find the rightmost one here. And what we need to do is to change this one to 0. So in this position you want to put 0. This prefix is the same. So this prefix stays the same. In this position you want to put 0. And in these positions you want to put all ones. Like you decrease the number by 1. You get the last one, decrease, and here you have all ones. Yeah? But now you don't want to have all ones, but you only have ones in positions where there are positions in x. So here you have. So if you just transfer all ones from x to here, like this. So what is the easiest way to calculate this new y from the previous y? Well, it's quite simple. You just have number y minus 1. In number y minus 1, you have 0 here and all ones here. And now you want, from these ones, you want only the ones which have ones in the same positions of x. So you want this ones from x transferred to here. It's just simply by ending these two numbers. So just y minus 1 and then end it with x. I don't need That's all. That's how you move from one y to the next one. And you will only iterate over all subsets of x. So here you just write something like this. Let's write it in C++ way. You do it like y equal to x, then y greater than 0, you don't do anything. And then you move by simply saying y is y minus 1 and x. That's how I usually write it. That's actually working code. Why do you need two ends? I need two ends. It's bitwise end. Yeah. Cool. So in this way you solve the problem in time complexity is 3 in power of n. And that's better than 4 in power of n, but still worse than 2 in power of n. Arithmetics is a nice science. Can we improve it even more? It turns out somehow we can improve it even more. For example, in this problem, we can do even better algorithm. It's not always happening, but in this problem, it's true. We can do even more efficient algorithm for this problem. But this technique is quite universal. When you want to split some set into some subsets to maintain some property, you can do it like this. It's a pretty universal way to solve problems like when you have a subset, you need to split some set into some subsets in some optimal way. Yeah, but in this problem you can do even better. How can you solve the problem better? Before you talk about how can we improve this, let's talk about why it is so slow. It is so slow because the number of states here is 2 in the power of n, right? The number of states of dynamic programming is 2 in the power of n. but time complexity is 3 in power of n. That's because we have too many transitions from one state to each other, because on each step here, the number of transitions, number of previous states of dynamic programming is too big, because we just iterate over the whole set. When we move from one state of dynamic programming to another state, we make very big step. We just add a lot of elements on the single step. And to improve time complexity, we want to get rid of this. We want to, on each step of dynamic programming, we want to add only single element. So we want to, here we add elements in groups. So each time we have a group and add the whole group to the current state. And I want to add elements one by one. So when I transfer from one state to each other, I want to add only one element to the subset. Cool. So how can you do this? You will do this in the following way. If you add elements one by one, then what will you have? So let's say you add this subset X to some knapsacks. So you add some elements here. Now you stop this, add some elements here, add some elements here, and some elements here. So these knapsacks are full, so you just close them. This is the closed knapsack. It looks kind of strange, okay. It's time to not run. That's not how the closed knapsack looks. Close enough. Well. But this one is open, so you put the next elements here until it is full. When it's full, you close it and move to the next knapsack. So what do you need to know about your current state when you have a situation like this? You want to know the total number of knapsacks you used and the total size of elements you put in the last knapsack. So you need to actually have two parameters. What is this? Here we have two parameters. First parameter is the number of knapsacks here. Let's say it's A. It is the number of knapsacks you used to put all these elements. And the second parameter is the number, the total weight of elements here. And for each subset X, we will have this pair A and B. Again, for each set X, we will remember the pair of integers. First integer is the number of knapsacks we used, and the second integer is the total weight of elements in the last knapsack. So the last knapsack is not full yet. We can add more elements in the last knapsack. But these knapsacks are already full and we close them and ship them. So these knapsacks are full, you only can add elements in this last knapsack. That's all. Now, how to make transitions? It's quite simple. So imagine you need to make transition from one state to each other, to another state. So you have some subset X, and you want to make a transfer from some subset from X without number, without element I to subset X. So you want to take this subset, add element I, and then get to this subset. How to make this transfer? You get this state, get this pair, then try to add to this situation one element I. You add this element I in the last knapsack. If this knapsack is full, so you close this knapsack and create another knapsack and put this one element in the next knapsack. So when you prove this element, it's like this. So if B plus weight of I is no more than S, then you move to the state A and B plus the weight of I. And if it is more than S, then you create a new knapsack. So you have A plus 1 knapsacks, and put this one single element in this last knapsack. So this is the transition. It's kind of more complicated. Yeah, you have two numbers now. You need to make some strange code to make transition from one to another. You need to make another if here to just check which state you are. But you have only two transitions, not 2 in power of n transitions. Yeah? So the total number of transitions in your dynamic programming, transition from one state to each other, to another, is decreased. Yeah. That's all. Why do you? Oh, yeah. I forgot to mention this. Oh, a little bit of time. Here, I want to optimize two variables at the same time. I want to have the smallest possible number of knapsacks from one hand, and on the other hand, I want to have the minimal possible sum in the last knapsack. So I kind of want to optimize both these numbers. Sometimes it's happening. Sometimes you kind of want to. You have two parameters, and you want to optimize both of them. And usually, it turns out that you cannot do it. Because you if you optimize this will be large. If you optimize this will be large. Yeah. But in this situation, it's actually possible. In this situation, you can say that you want to optimize A, number of knapsacks. But if you have the equal number of knapsacks, you want to optimize the parameter B. So you want to minimize this pair. You want to minimize A and then minimize B. Why is it true? Because let's see what does it mean that we have the better situation. Let's say, how do we compare two situations? What situation? Y1 B1 and A2 B2. Let's see. Simple case. So if we have small number of knapsacks and smaller amount in the last knapsacks, then it's absolutely better situation. Yeah. So if A1 less than A2 and and B1 less equal B1 less equal than B2, then obviously this situation is better. Yeah. We have less number of knapsacks and less amount in the last knapsack. If it is the same, and it is included in this. What if this doesn't hold? What it means? It means that, for example, if one is less than this, but another is greater than this. Yeah. Which situation is better? It turns out that this situation is always better. Why is this true? No, simply because of the following resources. Let's look on the first situation. You have some number of knapsacks. Yeah. A1. And in the second situation, you have some another number of knapsacks, which is greater than that. Yeah, including this. What we can do in this situation, we can just close this knapsack and have another empty knapsack. Empty knapsack here. And my situation will be better than that situation. So my situation A1 B1 is better than situation A1 plus 1 0. Yeah. Just because I can close the last knapsack and have one empty knapsack. I have one more knapsack, but the last knapsack is empty. So I can get from my situation to this very easily. So my situation is simply better than this situation. And this situation is obviously better than this situation because A2 is greater than A1. So this is greater than A2 B2. That's all. So that's not very usual case, but sometimes it's happening. So you have two parameters to optimize, and you have some priorities. So you want to optimize first parameter and then optimize the second parameter. Just because you can compare two pairs, because for each two pairs you can check which pair is better. It's not always true. Sometimes you have one pair with one better parameter, another pair with another better parameter, and you can compare them because each of them may be optimal in future, depending on what's going next. But in this case, it's true. And now we just, again, let's finish this. So now we write simple dynamic programming. For each step, we calculate this pair. We check on previous states, use this formula to calculate the next pair, and so on. In each time we find the minimal possible pairs. So we will have 2 in the power of n states. For each state, we iterate all elements in this state. So we'll have total complexity something like 2 in the power of n multiplied by n. And that's obviously better than all we did before. It's much better than 4 in the power of n. It's much better than 3 in the power of n. Whew. Okay, that's all for today. See you next Friday.